So welcome to the second day of the short course. And this day is a little bit, there will be two different topics. One is about functional regression, and the other one is about the registration problem, which are different type of things. And functional regression is something that's, at the moment there's a lot of work on that. Though there are many papers that just recently appeared in this context. And so what I present you is a joint work with Prof. Kneip and Pascal Zarda from Toulouse. And it's based on a paper that has just recently appeared in the Annals of Statistics. Okay, so what's functional regression? Well, in fact, the first time I ever met this problem was a consultation I did in Louvain-la-Neuve. There a firm came, as it was a chemistry firm, and they told me they have a chemical reaction that takes place in a reactor over 24 hours. And everything now depends on the temperature in this reactor over the time. And they wanted to know, but they can control this temperature, and they wanted to know what was the best temperature curve in order to have the best reaction. So the problem was you have a temperature curve observed over 24 hours. In principle, this is a continuous curve. You always have a temperature. Okay? And you have an outcome that was a chemical reaction, your y variable. And so you want to model your y variable independent of this function, of this temperature curve. Well, at the time they asked me, I didn't have a great idea what to do. I just asked them to do some basis expansions of these temperature curves and then to do some type of parametric modeling. But in principle, this is a problem of functional regression. But you have, say, a response variable y, for example, this chemical reaction, which depends on the variation of exponential variable x over time. And this exponential variable is supposed to be functional in structure. And for example, the first example is what I already told you, the chemical reaction, depending on the varying temperature curve over, say, 24 hours. Or another problem which I discussed with some people was the end price of an eBay online auction, say duration 7 days, independence of the price changes in the first 5 days of the auction. So you have the prices observed in the first 5 days, and you want to predict the end price. And there's another application, in fact there's a small application in this paper, which depends on the maximum of ozone measured during the day, independence of curves representing repeated measure of the concentration in ozone measured the previous day. That's based on some observations in the area of Toulouse, where they have a station which measures the ozone concentration, in principle on a continuous level. So over 24 hours. And the idea is, well, you have a ozone concentration curve from one day, and you want to predict the maximum level the next day. We've tried some importance because they have, if the ozone predicted is too high, they will perhaps have some measures to say no traffic in Toulouse. Okay, so these are the type of applications in this context where you say, okay, that you have some observed curve. Well, usually in practice, of course, you will have observation at discrete observation times, right? Not just a continuous curve, but discrete observations. I know this number p of observations, of discrete observations per curve, and usually I here assume that p is very large. So, in principle, you could just write it down as an ordinary multiple regression model. Say this constant plus some j is 1 to p, coefficient beta j, times the value of the curve at the observation point tj. Like a usual regression problem, where you have one variable is income, the other is age, the third is family size. It's only here your variables have the special property that they are observations of a continuous curve at observation times tj. So they are all related, right?
So we have n experiments of the same thing, and n experiments, and each of experiment is observed in p points.
Yes. You have, for example, consider this chemical thing, right? You have a chemical experiment, and you have a certain temperature curve that you apply. They can't control that. Okay? So you have a varying temperature curve for 24 hours. Now, of course, in order to manipulate it, you cannot really work with continuous curves, and the computer won't accept it. You have discrete observation points, say each hour. Then the p will not be too large, okay? But could also say each minute. So the first variable is, for example, the observation of the temperature curve first minute. The second variable, observation of the temperature curve second minute. And the third, J, is the observation of the temperature variable fourth minute. So in principle what you write down is an ordinary regression model. Now with these p explanatory variables, where each explanatory variable is the temperature curve in a certain minute. Yeah?
Is it also possible to consider the case where the observation times depend on J, on I, sorry?
Yes, of course. That's not a real problem. It's just to simplify these things. I mean, in these many applications, this content they will have the same ones, but that's not necessary. It's not necessary. And there, of course, are cases where this is the case, where they depend on I. In fact, we will see that's only a little bit to introduce that. We will rewrite this model in a moment, where you can see that it doesn't matter so much. How it is explained. But so you have to keep in mind, in principle it belongs to the class of problems where you have an ordinary regression model with standard error terms, which are, say, homoscedastic and everything. Only you have a lot of explanatory variables. Right? And in this context they are functional. So they are the observations of a curve at different time points. Yeah? But you have many observations, and very often p will be larger than n. Right? Which of course says, well, you could say, you write this down as an ordinary regression problem, but you can't estimate beta 0, beta j bar e squares. Because if p is larger than n, well, you're dead. Yeah? Okay. It just reformulated now in a continuous version, where just this, which makes things a little bit simpler. Also, it doesn't depend so much on whether the observation points are equally spaced or the same for all individuals. So the functional regression model would be something like that you have a scalar response variable, as for example the outcome of a chemical reaction or the end price of an eBay auction. And the variation y is model independence of a functional explanatory variable, and well, okay, which we assume has all nice properties you need. Okay? And so usually, the usual setup would be that this is a sequence of identically distributed random functions. Okay, in the functional linear regression model, well, essentially you could say, okay, that's something, what here you have is something like a Riemann approximation to an integral. Because you have something like, these are just discrete measurements of a curve at discrete time points, and if p is very large, this will be close to the integral. Okay? And so you could write it in the way that it's just an intercept, plus now you integrate a slope function. This is now a whole function, beta of t, right? This is the beta j, is in principle beta tj, depends on the observation time, times the function xi of t dt. Okay, so we have, this is the usual thing of a functional regression model, which is just, makes it simpler if you write it down in this continuous version. Okay, and so your task in this context is to estimate the slope function. Right? So it's not only a number of parameters. So in this functional regression model, even if you see the betas, the number of parameters you have to estimate is in principle infinite. Okay, this is very large. And apart from that, I here assume it's a standard regression model with homoscedastic errors. Well, the only speciality is this type. You have a functional explanatory variable and the corresponding slope function, beta t. Well, I just want to mention, of course, if we go down to that, there is a lot of literature now on high-dimensional regression problems, where you have a lot of different explanatory variables, and where, for example, p is larger than n. And of course this is related, and there's a lot of literature which is sometimes called a sparseness literature. The methodology they apply, I don't know whether you are in it, so it's lasso, Danzig selector, things like that. And so they also consider this type of problems. Usually, okay, I have dropped the intercept to make it simpler, that you have a lot of explanatory variables, which now usually in this context they don't give a specific structure. In our functional context, each xij is just the observation of a continuous curve at a certain time point. This generally in this literature it may be something, yeah, many different variables. Usually they don't suppose structure. The assumption they have in order to apply their methods, for example, the famous methods are lasso, I think this is the best known, the Danzig selector, which has received considerable attention in recent time, and their theory is based on some assumptions. One of them is sparseness. There's only a small number of these bit coefficients which are non-zero. Usually, so the influence of most variables is negligible. And you only have some variables which play a role. And the second assumption, which is often hidden, which they don't really talk about a lot, is that what you need is that you have sufficiently weak correlations between the xij. That's a very important assumption. For example, Cantor tells say every set of columns with cardinality less than Q, what is Q? It's number, essentially here the number of non-zero coefficients, has to behave like an orthonormal system. So that essentially the x's have to be something like closely independent. There may be some correlations between, if you just say, if you have 3 or 4 explanatory variables, they must be almost independent from each other. There may be small correlations, but they cannot be large. Otherwise, this theory doesn't really work. In the functional context, with these functional regressions, we are in a different world, where this method don't work at all, because neither of these assumptions is satisfied. The point is, if you rewrite this, to be more precise in these things, you have the model would be this integral here, okay? So you have the slope function. If you rewrite that more precisely in a discrete setting with discrete observation points, it would essentially mean that the true beta j, the slope function you have, we have to divide by 1 over p. This is the Riemann integral, the Riemann approximation to the integral, with the xitj. Which means that in a way, if you write the coefficients this way, you have something, h beta j will be the slope, the value of the slope function beta divided by p. Just to this Riemann integral. Okay? So what you will have in general, that all coefficients beta j will be the value of, in this model, of the slope function, just to go back, of the slope function beta g in this continuous integral divided by p. Yeah? Just because this Riemann integral will approximate, this Riemann sum will approximate the integral. That means all betas you have here in this model, if it's a functional conversion, will be small, but will be of comparable order of magnitude. There will not just be a finite number which is non-zero. Essentially, practically all coefficients will be non-zero, but they will all be small. And the other thing is, of course, also our explanatory variables are the observation of a continuous curve at different time points. And these observations, if you have time points which are close, the correlations will be extremely strong between these between these x's. So if, for example, if you consider the correlation between xi of tj and xi tj plus m, if m is some point a little bit apart, if as peak to infinity and you get denser and denser grid, this correlation will go to 1. So neither of these assumptions is fulfilled. So this theory with lasso and so does not apply in this context.
I agree with this argument, but It seems to be a matter of your way of approximating the integral by the sum. So you just approximate the continuous integral by Riemann sum, but you can do kind of Fourier expansion. Say it's another approximation of
Yeah.
the integral by a sum. Is that?
No, you're right. You're right. I mean, I will come in a moment. Just what you can do is just functional regression, then you have some sparseness. I mean, in a way, it's just what I want to say in this context directly. If you have these explanatory variables, there's no sparseness involved.
But it's just because you select a very strange way of coding your model. By very close points, and so this is just for this particular way of approximation of your integral by a sum, these conditions are not fulfilled, but it's not
oh well, these conditions are very strong. I mean, why should they be fulfilled in practice? Almost independent explanatory variables. Where in the world, if you have 10,000 explanatory variables, they can't be.
For instance, if you decompose your integral and say Fourier sum, then this would mean that most of the Fourier coefficients are just zero.
No.
This is sparse that it could be fulfilled with no big problems.
No, there's another type of sparseness which is true. I will show that in a moment. Yes, but that you have to do the approximations, but not with his sum, right? And I also think that in practice, this is a very hard restriction. Very hard restriction. Not so flat, perhaps. The sparseness is one thing. Some type of sparseness must hold, otherwise you can't work with high-dimensional problems.
It's not a restriction, it's an identifiability condition. If
This
hold, you cannot estimate beta, just identifiability.
This is hard. This assumption of weak correlations. But there I'm just writing a paper with Pascal Zadar, where we show that if there are heavy correlations, there's a chance just to do some decorrelation with principal components, and then you can come into this context again for the decorrelated data. Yeah, that's what we try. So just on a step of factor model, and then do a decorrelation, and you end up with a model where you can.
This is the same what I am saying. So it's a matter of identifiability, therefore matter of parameterization. If you change your way of parameterization, you can get rid of this condition.
Yeah, okay. That's just what I wanted to say. You end up with type of sparseness if, for example, you consider dimensional reduction by principal components. That's not just one fixed space. As I told you yesterday, always principal components. The thing is, they give you the best base for approximating these things. Yeah. The disadvantage is an unknown base. Yeah, but it's so if you work with that, you try to use the best base for approximating functions. And so, for example, if the discrete case, you have the covariance matrix of your xi's. It's all the things I discussed already yesterday. And if you have in the continuous world, you have then the covariance operator. And so you have the eigenvalues and the eigenfunctions of this gamma. And if X is smooth and equidistant design, you can show under some regularity conditions the eigenvalues here divided by P will converge to lambda r. And also the eigenvectors suitably standardized will converge. Their results would show that this is generally true. And this holds in principle also for all P. Even P is much larger than that in this context. And you have some convergence in this respect. And of course this also gives you a way to access this problem. This is again this thing with the best basis property. If you have, for example, the k-first principal components, if they explain certain fixed percentage of the variability of X, then the principal components give you the best k-dimensional linear space for approximating your observations. And just the approximation error is just the sum of the remaining lambda j's. Okay, but this is, I don't want to go into this detail anymore because we discussed it yesterday in detail. And of course, one of the popular methods in functional regression is just to use that and to approximate everything in terms of principal components of these functions, because you can rewrite, of course, now, that's what you say, with the x's, that's perhaps, this is a better way to rewrite that. So, if you have, for example, if you knew the gammas, and this is just the inner product of xi and gamma, just the integral of the product of the two functions, and you can also, so you can expand your x's in terms of the principal components, of the eigenfunctions of gamma. You can also expand your beta, your slope function, in terms of this basis, the gamma, and then you can rewrite your regression model in this form, that yi sum r is 1 to infinity, beta r, delta r plus epsilon e, where beta r is just, say, the coefficients of beta when you when in the approximation by beta in terms of physical components. You have something like that beta of t is then something like some r is 1 to infinity, what I call here beta r times the rth eigenfunction. So you have an expansion in this context. And these are the coefficients of the betas, and the deltas are the coefficients of the xi. Okay? So you have something like new explanatory variable. That means your the coefficients of the approximation of xi in terms of the function of the eigenfunctions and the corresponding beta r. And there, if you have some, it's quite clear, because the influence and the importance of principal components decreases as r tends to infinity. And if you then say, well, okay, at least all the betas are bounded, then necessarily in this term some of the betas will be very small. So you can essentially say, well, I can stop here at a certain k. The rest will not be very important anymore. And so the usual approach to estimate in this context is, which is used by quite a lot of people in functional regression, is to use principal components. That means estimated principal components, of course, from the empirical covariance operator. You don't know the truth, which are determined from this type of model, where you just don't go to infinity but to a fixed number k. And the k is something like a smoothing parameter in this context. You don't want to go too far. If you go too far, you add too much variability. You have too much to estimate. If the k is too small, you may have a bit bias. So that's the usual type of problem you have. So these deltas, these are determined from estimated function principal components, and then what you do there is essentially you estimate the betas by least squares, essentially, which is okay in this context because also the delta will be orthogonal. The vectors delta will be orthogonal to each other. Okay, and then your estimated beta hat is then using this decomposition. That's the estimate of the slope function. You have here your you just stop at k here, and you replace the true beta by beta hat, and of course the true gamma by the empirical eigenfunction. Okay, so that's the usual approach, and there are also theoretical results in this respect. So for some k and tau, we derive rates of convergence for the difference between beta xt and beta hat xt for a pre-specified fixed function, so something like a prediction error for a fixed function, fixed new function. And Hall and Horowitz provide optimal rates of convergence for the L2 distance, beta minus beta hat.
The question is how far you can go with this method. For instance, this popular case, P larger than n. What would work there? Because you also need to estimate the principal components.
Yes.
And if you have only n observations,
Yeah.
and n smaller than p,
Yeah.
then your principal components will be automatically in the subspace generated by the beta.
Yes, but you can show the first. It's no problem to use at least if you use as long as the lambda, you want to, you can't of course estimate all principal components at the same time. That's impossible. But you can estimate the largest ones. Yeah? And where you can show there are really now very explicit results on the rates of convergence of these things. You can go as fast as if you have something like, for the two principal components, you have lambda 1, lambda 2, and so on. And there's no problem for estimating that. The precision will be sufficient until you have something that if lambda r, something is of the order of magnitude 1 over square root of n. Then it's okay. Up to that it's okay. If the for principal components where the lambda are still smaller, there are some problems. You can, under certain additional assumptions, you can go as far as something as 1 over n log n. But this needs additional assumptions.
But what do you mean no problem? In terms of the rate of convergence or for practical applications?
In terms of theoretical behavior.
So
In terms of theoretical behavior.
My experience is strictly against principal components in high dimensions. But
Well, it depends. The first ones are usually very quite well estimated. What the people usually do here, I mean, there are theoretical results concerning K, optimal rates of convergence. Most people who apply that use 3 or 4 principal components, which is usually okay in terms of the behavior. The first one is usually very well estimated, and the second one too.
no, I think the real problem is typically that so what you observe few vectors, n vectors in very high dimensional space. And
Yes.
and then later you only stick to this subspace in which your data is. This is what the principal components are doing. So in the subspace generated by the data, you look for the principal components. But this subspace is very random. And this induces a lot of variability in the resultant procedure.
Well, this depends, because usually what's not so variable, you're right in so far that very often what is the principal component? And that is quite random. And for example, if also lambda 1, lambda 2 are close, there may also be changes. For example, that in the estimated ones, the second may be the first, and so on. But what's quite good often is just the approximation space of a great number of the principal components.
Okay.
That's usually very often not bad. Good approximation.
I see your point. And another question is, even in high-dimensional space, if you look at the microarrays analysis, so what you are interested in the coefficients in the original basis. So genes. You want to know which genes are significant. And this is the betas in the original parameterization, the beta of t. And so after changing the basis, you can well estimate the other coefficients which are in your expansion, but they don't really tell you much about particular value of beta of t.
Okay, this is not about genes here. This is about functional regression. And there will be no single observation point, usually, which will be significant. It's really the function that pays. So there's nothing, what you say, a particular xi, tj. Yeah?
So you mean you are looking at predictability in terms of these integrals?
People also look, and so the model is, again, this is the beta 0 plus the integral, beta t, xi of t, okay? And there are of course, two points of view. One important one is prediction, yes? The second point is you may want to know the slope function here. Yeah? But usually the idea is not that one, so the discretization is you have xi of t1, xi of tp. Okay? And the point is, of course, usually we will not have the idea that one of these points plays a particular role. So you are not interested in the significance of a particular variable. It's the curve as a whole that plays a role. And so, of course, it's reasonable to ask, how good is this slope function estimated? Just for modeling. That makes sense. The problem of estimating this well and doing a nice prediction concerns this term. You have to estimate this term well, is a different problem. And you can show that methods which are good for prediction usually don't give the best possible beta estimates. That are two different problems. So prediction and the best estimation of beta is completely different.
Can I ask? So in the model specification there, the principal components and the eigenfunctions are computed from the x-size. So the delta, some
Yes.
point delta will go to 0 or
Yes.
very good. Whereas a beta corresponding to that,
Yeah.
so why should we expect that corresponding delta also will go to 0?
That's usually assumed. Well, I mean, there's one thing you have a little bit to notice the standardization of this whole thing, right? If you rewrite it in this model with the beta, okay, then what you will have is something. For example, if you compare to the lasso literature, that is say all x variables have the same scale, yeah. So the norm of x is 1. And if you renormalize, because the deltas here will have variance lambda r, and lambda r will be small, right? And so if you bring all regressors on the same scale, it means that you rewrite this thing with a delta A star, which is delta A over lambda. Then the delta A star is variance 1, right? But this of course then means that you, in order to have the same product, that you have beta stars lambda times beta, right? So if you bring all regressors on the same scale, this means, relatively speaking, that you now have another beta, which is lambda r times beta r, and lambda r will be 10 to 0. So if you have the general idea, all betas, which are in here, are at least bounded by a constant, right? This would mean in this type of regression, there will be very few beta stars will play a role.
Very few what?
There will be very few beta stars which will be large. Yeah, because these beta stars, if you really renormalize all the variables on the same scale, the corresponding betas will decrease with R. It makes some sense, but this is usually assumed in this context. But I want to speak about mainly about what we do, and we have another approach. We don't use principal components. We use spline estimators for the betas. And I think for prediction, at least, it is much better. It also behaves quite well. So what we do is the following. We assume that, well, our estimate is directly based on that we have an observation at, say, p equidistant time points. You can also modify that if you have random design. It's not so much of a difficulty. But just to present it in a simple way, we have also the time of t1 to dp. They're all the same for all the curves. And our estimator of beta is something like a spline estimator. So we determine an estimate beta hat of beta with independence of the smoothing parameter rho by just considering this residual sum of squares. The y tildes are just the centered variables where we subtract the means in order to get rid of the constant, which is later on, in order to get rid of the intercept. Yeah? So we just we go y tilde I is yi minus y bar. Subtract the means. So what you see here is just something like the residual sum of squares for a fixed beta, for a fixed b. And now we have here penalty, which is just, we say, well, we now penalize non-smoothness of the slope function. You see, that's the model. You have your slope function. You, well, shouldn't be so too wiggly. And so this is something like a spline penalty here, which is just the integral. We say the interval is 0, 1, so the mth derivative of t squared. That's the penalty. We also have another penalty, but this is more for technical reasons, where we penalize this thing p is just a projection of the best possible approximations by polynomial of degree m minus 1. In principle, for usual spline estimators, this wouldn't be there. This is there because otherwise you have technical difficulties that the estimator may not exist always. But it's not very important from most points of view. It depends also on the structure of X, or whether whether it's reasonable to include that or not. It's just a theoretical tool to guarantee existence of the estimator. Okay, and so we minimize this thing over all functions within the suburb of space and so on, as usual for splines. The point is, the solution of this thing, the function that comes out, will always be a natural spline, because we have here the p time points. Why a natural spline? Because, well, what you see here in this residual sum of squares, only the values of the function b at the observation points, tg per year. So the values in between the tj, they only enter here in the integral, in the second derivative. And and of course, in principle here, there may be now different functions which have the same values as the tj's, but differ here. And there's this property of splines that they use, that they give the smoothest interpolation. So that's the reason why the solution of this is always a spline function. So any solution has to be an element of the space of natural splines of order 2m with not that's t1 to the tp, which is a p-dimensional linear space of functions. And the reason for that is the important property if you have compared two functions which have this at your observation points, adopt exactly the same values, then the spline interpolation between is the smoothest possible interpolation, which gives the smallest integral in your penalty. So the function which comes out in this penalty will always be a spline, because it will, from all points which have the same values here, it will give the smallest possible value.
But then in the original sort of high-dimensional setting, you will just convert to the rich regression with a smart penalty.
No, that's not a rich regression. No, that's spline. That's smoothing spline regression in principle.
No? Can we view it also as a rich regression?
Well, it depends how you define rich regression, okay?
If you parameterize your space of splines, then you can...
Well, okay, but then you have to reparameterize that and say what are the basis expansions and the eigenvectors and so on.
And then you can represent.
At least it's not rich regression in the ordinary sense. You know? I mean, okay. It's just usually that's just smoothing splines, right? So you know your smoothing spline estimator. You have here my data. The only thing is, of course, you would not usually not have here this Riemann sum, this integral. You would have just yi minus the value of your function. Yeah, that would be.
In a sense, without penalty, it would not, the estimator would not be computed, or whatever the singular, the inverse matrix. So
yes, this the inverse matrix may be singular. That's why we added that. Just to ensure that the matrix is not as a singular. That's why we had this strange term here with this pi, just to ensure that always our estimator exists. Okay? And the thing with these splines is, well, as I said, the solution is necessarily a spline function, and there exists a canonical one-to-one mapping from Rp into this space. And so for any vector, W1 to WP, there exists a unique natural spline interpolant which just determines at the observation points you get this value as WP. And you can also, in the matrix notation, WP can be written in descent, where this is the A matrix is determined from spline basis. And okay, so you can also rewrite the problem. You just minimize the beta hat over, you just look for the vector beta hat, this beta hat T1, beta hat TP, which minimizes this thing, where the SM is the natural spline interpolant. It's the spline interpolant of your beta of this vector, yeah, at the observation points. And your estimate of beta will then be determined from this vector, just interpolate using splines. Okay? And of course, this vector is this thing because in principle this is now a vector problem. You determine a vector, beta hat T1, beta hat TP. This can be rewritten in matrix notation. And just to give you the explicit solution, where we have the vector y of the y's, 1 to yn, the vector of our x's, x1 to xp. The betas are the vectors of the betas at our observation points. And we have here this type of projection matrix, which comes from the P. Then, and also for the natural spline interpolant, this can be rewritten in matrix form, depending on the value of P. And so with Bm is Pm, this projection matrix that comes from the approximation of polynomials, plus P times Bm star. This is this matrix of second derivatives of spline interpolants. As a matrix problem, this is just minimize this thing, the matrix term y minus xb plus rho over p times this matrix here. This should be a minor p, not a capital one. Okay, and then your estimate can be written in the form beta hat is determined by multiplying this matrix here with your vector of observations y. And just what I said with this polynomial approximation, this thing with the projection matrix guarantees that this always exists. Because otherwise, the point is that that usually these spline matrices here, they have two eigenvalues equal to 0, which correspond to linear approximation if you have cubic splines. So, if you only use this matrix as eigenvalues equal to 0, and then it would depend on the structure of X whether or not this thing exists. With this projection, it always exists. And so beta hat is just the spline interpolant of this vector we get out, constitutes our final estimator of beta, and now we have here subtracted the means. Beta hat is y bar minus beta hat x bar estimates the intercept. And all eigenvalues here of this thing are strictly positive. Okay, so this is our estimator, and in principle it's not easy, not very difficult to implement. There are very nice implementations of spline smoothers, and this is easy to adapt. Okay, give you some results in this direction. Well, what our focus here in this paper lay upon the prediction error. That means how good can we determine this term here for new function x? Right? So this was the main focus. There's also, for many applications, I think prediction is an important thing. And the asymptotic performance of the estimator is evaluated with respect to its prediction error, which means that we will write it in this way, that we consider beta hat minus beta in a special norm, which we call the gamma norm. This is an L2 seminorm defined by U2 gamma is gamma U. And you can easily see that this difference here, I see there's something missing, that if xn is a random function possessing the same distribution as xi, but independent of the sample xn, then this type of prediction error, beta hat minus beta hat xn plus 1, so if you have a new random function, for a new function you get, and you want to see how good does it predict what is the difference between beta hat 0 plus beta hat xn plus 1 minus, if you here use the true parameters, that's a prediction error. Okay, this is just, now you don't see it again, this is just the difference between beta and beta hat and beta in this norm. No, well, squared. Plus something which is OP n to the minus 1. Okay, so that's the term we consider. How big is this difference? If you have a new function, xn plus 1, which has the same structure as our original sample, but is independent of our sample curves, how well can we predict these values here? So how good is our prediction? Okay, in this context. And there's some assumption. So if we assume for something like beta is m times differentiable, and beta m belongs to L to y, and do some Lipschitz continuity for x, which is mainly important to show the convergence of a Riemann sum to the integral. No, it's okay. I mean, I don't think it's such a problem. It only happens once or twice that there are something just down. Okay, and then we assume that for some constant C5 and OK, there exists a k-dimensional linear subspace Lk of L2, such that the quality of approximating X by such a linear subspace is of the order k to the minus 2q. So if you increase q, if you increase k, say you get better and better approximations of X, and the rate of decrease of the error as a function of k is depends on q. Well, essentially you could say this again means, well, if you have the principal component of X, this is exactly then the rate of decrease of the sum of the eigenvalues, of the smallest eigenvalues. Okay, you have to remember this q. This is just the quality of approximating X by a linear subspace with k components. How fast does it decrease if I increase k? And this is a more technical condition which we need, which is satisfied of, for example, Gaussian distributions or many others. I don't want to discuss that. Discuss this, for example, this q can be related to smoothness of X, of your functions. There's just by Jackson's theorem that, for example, if you have something like that X's are almost q1 times differentiable and there exists a constant such that the Lipschitz condition is fulfilled for this thing, then this quality of this linear approximation is given by, at least by, to the k to the minus 2 q1 plus q2. For example, this means in this context, if, for example, your observed functions, which you consider at least twice continuously differentiable, this q is at least 2. Okay? If they are 4 times differentiable, this q is at least 4. And if they are 10 times differentiable, this q is at least 10. This is quite important because this enters into the rates of convergence, this q. What's important, the m is the degree of smoothness of beta, which comes into play. And in a way, this best approximation, which, for example, if the x's are 4 times differentiable, it's at least 4. But I mean, there can also exist very well approximations by such linear subspaces, even if the x's are not smooth at all. You have curves with jumps, who nevertheless are well approximated by where the q is nevertheless 10. Yeah, so that's not the thing. Okay, and so now what we get in this thing is now the difference between beta hat and beta and this gamma norm, which is just a prediction error. The difference between essentially the integral of beta hat x n plus 1 and beta hat and beta, and the true beta, is of this order. It's of order rho plus there's something like n 1 over n rho to the power of 2m plus 2q plus 1. You see the m, that's the degree of differentiability of alpha, of the slope function, and that's the q. For example, as I told you, if the x is at twice differentiable, q is at least 2. Or if they are 4 times differentiable, q is at least 4. And this term is will be negligible if q is at least 1. Okay, so you should forget about that. And so this means that for out of sample predictions, the quality of your prediction depends on now has this non-parametric rate of convergence. So there's a difference because usually if you have an ordinary multiple regression where p is much smaller than n, and p remains fixed, then usually, of course, the quality of prediction will be, if you have the squared error, it will converge with 1 over n to the minus 1. But in a functional context, it's like if you have a smoothing problem, you don't have the parametric rate of convergence, you have a non-parametric rate of convergence. And this non-parametric rate of convergence here depends on, now you see, so usually if you choose an appropriate smoothing parameter, n to the minus 2m plus q to m plus 2q plus 1, it will be of this rate. Depends on m, depends on q. And this is the higher degree of the differentiability of beta, and for example this quality of approximation of x by k-dimensional linear subspace. Or if they are 10 times differentiable, this is quite high. This will be close to n to the minus 1. But this is a non-parametric rate of convergence. Okay? And it's not a parametric one. And we can also show that this is an optimal rate of convergence. So there's no other estimator which can achieve a better rate of convergence. Yeah? So under some condition, this is an optimal rate. So it's the minimax rate. And okay, just to hear a little bit about the results of k and tau. What we consider is just a regression error. We consider how good can we approximate beta t xn plus 1, okay, of t dt. So the result of this integral by the thing where this has a head. So for a new function, random function of the same structure as the sample which we consider, k and tau consider another prediction problem if you don't have, say, a new random function of the same type, which qualifies as sample, but if you fix a function, say, I want to predict what happens integral beta t, and I use small xt at sinus t. What happens there? And there, of course, what they get out, the rates, then depend very much on what's the structure of the function you consider. Depends very much on that. They say, for example, under some, and in principle, it depends very much on how well this function is approximated in terms of here of the space, in terms of basis expansions, in terms of function principal components. Whether this is well approximated there or whether the approximation doesn't increase rapidly, they show that for some functions we get the rate of convergence parametric one, n to the minus 1. And well, I don't want to discuss that in much in detail. The problem is the functions for which you obtain n to the minus 1, if you have the problem that you have a new random function, then the probability to have such a function is 0. Yeah, so the point is that the probability to observe a function which has this particular structure, they need in order to have a parametric convergence. And if you have a random sample and you observe a new one from the same structure, then the probability that it will satisfy these conditions is 0. So simply won't happen. Okay? So one remark in this context about I told you we concentrate on the prediction error. That means how well can we predict this thing by using our estimate. So the integral beta hat of t xn plus 1 of t dt. Okay, so how well is this approximated by that? Now, of course, one can also reasonably pose the question, in many regressionists, either you're interested in prediction, either you're interested in modeling, and you want to know something about structure of beta. And now, what is, if I compare just directly beta? So, for example, if I consider the L2 distance between beta hat and beta. So what happens if I don't consider the prediction error, but something like the integral beta t minus beta hat of t dt. Okay? Which means I compare the betas, not a prediction. And this is a completely different problem. And usually it seems that a method which is good for determining this is not so good necessarily for determining that, for being good at that. In particular, under the assumptions we gave, where we have the optimal possible prediction error, we can't even guarantee that this goes to 0. Because we have not even a condition that guarantees identifiability of the beta. So the problem is that components of beta which are in the kernel of the covariance operator are not identifiable. Well, I mean, just to tell you the problem, for example, suppose that the x functions are such that, well, these are always functions which are orthogonal to straight lines. So if you integrate the x functions which you have are such that if you integrate it with a straight line, it's always 0. You just have to say they just have this property. Okay? Maybe, usually they won't, but maybe your x function of this type. Then of course it could be, generally, you say your beta, what happens if for any linear component of beta? Well, if your true beta has a linear component, well, in this integral, and that's the only thing which you observe, because the yi only gives you information about the integral of the beta of x. Any linear component will not play any role, because it's 0. Integrated with x is 0. So you will not observe it. It will not be there in your data. And so you can't estimate that. Yeah? So you will get no information about linear components of the beta in this thing. If all the x's are orthogonal, just that they are orthogonal to straight lines. Okay, this can be happen to not to straight lines, but to any other functions. So any component of beta which is corresponds to something that's orthogonal to all the x's, which mathematically speaking are the kernel of the covariance operator, will not be identified. So if you want to say something about that, at least you need something that ensures that beta doesn't possess any components of that. Yeah? So no straight line, just excluded. You have in a way then to ensure that the structure of beta and the structure of x fit together. Here it doesn't matter so much, because if there's a component of beta which is perhaps theoretically corresponds to beta but is orthogonal to x, then it doesn't influence the prediction at all. But if you consider these things, then that's a big difference. Okay? And so you get very different results. And also, for example, for a spline approach, the smoothing parameter, which is optimal for prediction, has nothing to do with the smoothing parameter that gives you an optimal here. Yeah, optimal beta here. Nothing at all. And so any results on the convergence of the beta hat in the sense of the L2 norm, if you don't consider the integral with x, so the prediction error, will depend heavily on how x and beta fit together. And you have to impose additional assumptions on the structure of beta, which are unverifiable, of course. Any assumptions on that, because the only thing you observe is this thing. So anything that concerns components of beta, which when you integrate it with x, disappear or are extremely small, will not be verifiable. Okay? So you have to add conditions like that. For example, Hall and Horowitz do that. They say something how well beta is represented in terms of an expansion in terms of the eigenfunctions of the covariance operator. They have to impose conditions there, and then they get rid of convergence. But what is very important in any case, what we can show in any case, if you do all that, it's still that an estimator minimizing beta hat minus beta, the difference with beta will have to rely on a rho that is much, much, much larger than our rho that is optimal for prediction. So that is, it's not very clear for me how to determine such a rho. Because, so that's a difficult problem, and it's also different from the prediction problem. I mean, that's a difference between all this and ordinary multiple regression. Their prediction and estimation of beta is about the same thing. Not here. It's a very different thing. And but the optimal rho for prediction, this is okay, because this you can find by cross-validation. So parameter rho, this is good for prediction, not for estimating beta. For estimating beta, you will have to have another parameter, because the rho that will that's good for prediction will usually give you a beta that's much too wiggly. That's just because if the beta has wiggly, has a lot of noise, well, integration will cancel noise. Integration with x will cancel noise out. So it's only important to have a small bias, in a way. Yeah, so it will be usually compared to a rho that is good for estimating, for approximating this difference, it must be, the rho for prediction must be under smoothing. And so we just have the usual cross-validation criterion, which can be easily rewritten in terms of our estimator, which is also easy to minimize. Yeah? So we minimize with respect to thing. You can also minimize with respect to the order of the splines. That's also okay. You can do that. And there also we have some theoretical results which say that this works. So that there is squared error for the estimated rho and for the optimal ones, this converges to 0. So as a n to infinity, cross-validation works in this case. Okay, but it will not work for estimating beta. Okay, we have some case of a noisy covariant which is not so much interesting. Okay, we have some small application about ozone pollution forecasting, where there's the Observatoire Régional de l'air en Midi-Pyrénées, where there are specific pollutants as well as meteorological measures are made each hour. And the exponential variable is a curve representing repeated measurements of concentration in ozone during a day. Response variable is the maximum of ozone to be measured the following day. And so after sending the x's, we have modelized the link between y by a functional linear regression model. And we're now interested in a prediction, also confidence band for the prediction, which is not so difficult. Of course, in order to have confidence bands, because, well, essentially, if you have for this confidence bands for y, we have a rate of convergence for this, so the difference will be essentially asymptotically small. And for confidence bands for prediction for the y, we only need a consistent estimate of sigma, which we get by this way. It needs to be shown this is consistent. And then our theoretical assumption by asymptotic normality of these things. And given down asymptotic prediction of the interval for the y1 plus 1 for new curve. Next day is then given by this confidence interval with the estimated variance and normal quantiles, and here you see some, well, maximum of the term predicted. Well, what we compare this, I have no slices about that, but we compare this, for example, for the maximum per zone. An alternative would be very simple. We just use the time series of the maximum ozone concentration each day, and use, for example, time series model, for example, the ARMA model for prediction. And there you could really see that, for example, when using the functional regression model, where you use the whole ozone curve to predict the maximum the next day, the prediction becomes, you win something like 40% in prediction accuracy, compared to just an ARMA model where you only use the maximum SJ. Yeah, where just the next day you want to predict from the maximum observed from the previous time series. So you really win a lot in this context. Okay, that's it.